Exercise 2 here is to implement the Gram-Schmidt procedure for obtaining a cube matrix from any other matrix. Okay, and here I have a little footnote here. It's footnote number 4. I write, take your time with this exercise. It's quite challenging. Now, the Gram-Schmidt algorithm for orthogonalizing a matrix, the algorithm itself in concept, in theory, is not so difficult. It's actually fairly intuitive, but all the mechanics, getting all the mechanics right is a little bit tricky. So this is not so difficult from the kind of theoretical linear algebra perspective, but it is tricky from the coding implementation perspective. So use a 4x4 random numbers matrix. Once you have your algorithm, you can check your answer against the output of numpy.linalg.qr. This is yet another one of these exercises, which I have in this book and in all my other books and courses, where it's super helpful for you to understand how orthogonalization works and how the QR decomposition works by implementing this procedure yourself in code. But that said, in practice, outside the scope of learning linear algebra, when you are applying linear algebra, it's always better to use QR decomposition that NumPy provides. And that's basically because the Gram-Schmidt algorithm on its own, the way I described it in this chapter, can be numerically unstable. So it's not necessarily the best procedure to use in practice. There are more sophisticated algorithms that are more numerically stable. Nonetheless, I hope you enjoy or have enjoyed working through this exercise. I think it's a really great way. Once you solve this problem, you really understand for the rest of your life, you will understand exactly how to orthogonalize a matrix. That's a really useful skill to have in your head. Okay, now about the Gram-Schmidt procedure, and in particular, the way that QR decomposition is implemented in modern computing involves a sign uncertainty. So this means that vectors can flip, so to speak, means that the entire vector is scaled by -1. And I'll talk about this more later when I show you the code and when I run the code, because we'll see these sign flips. But so basically what I want to highlight here is I'm going to talk more later in the book about exactly why these sign flips happen and what they mean and how to interpret them. For now, suffice it to say that you just need to be aware that there are these sign flips. Okay, so now I'm going to switch to Python and show you my implementation of the Gram-Schmidt procedure. So we start with a random numbers matrix. It's 4x4, but I set the code here to be M and N separately so that it is possible for you to adjust this code. So you can run the Gram-Schmidt procedure for a tall matrix or for a wide matrix. That's really useful for exploring how orthogonalization can work for non-square matrices. Nonetheless, for this exercise, I think it's best to stick to a square matrix. Okay, here I'm initializing. So we start off with a random numbers matrix, and this is going to be Q. We're going to fill in this matrix. We're going to create this Q matrix, this orthogonal matrix, one column at a time. Okay, here's the Gram-Schmidt algorithm. I guess I was too lazy here to write out the whole 3 words. Anyway, so we loop over all of the columns. And then here for each column, I'm initializing. So I set Q, this column, and Q to be this column of A. And now just for convenience, I'm calling this column of A little variable A. That's basically just so I don't need to keep writing out all of these characters over and over again. Okay, so remember the idea of the Gram-Schmidt procedure is each column in Q is orthogonalized to all the previous columns in Q. So we don't orthogonalize to future columns, we orthogonalize to previous columns. So that's why we have this loop here. So this is a loop for I, and here is a loop for j. And now j is always going to be less than I. So we're always orthogonalizing to earlier columns. Okay, so this is the column in A that we're orthogonalizing to. And then here is the column of Q, the current column of Q. Again, I'm setting this little variable here just so it makes this line of code shorter, basically. Okay, so here I have this column of Q, and this is the column of Q that we are orthogonalizing, that we're working on. And here is the loop over all the columns that we are orthogonalizing relative to, all the earlier columns. Okay, so it's this column here, and then we orthogonalize out the previous column of Q, which is here. So I hope you recognize this formula here. It's the dot product of A and Q divided by the dot product of Q and Q. So this is basically the mapping of A and Q scaled by the magnitude of Q, or technically magnitude squared. Okay, so this is something you learned in the orthogonalization section on the chapter on vectors. So this is the scalar to map Q onto A, and then here we scale Q. Okay, so this is the parallel component of Q with respect to A, and then we subtract off the parallel component, and what that leaves us with is the perpendicular component. Again, this is exactly the procedure that I taught you in the chapter on vectors and the procedure for orthogonalizing vectors. Okay, so then we basically just keep redefining the ith column in Q according to, or by subtracting off these parallel components of each previous column in A. So quite confusing to say, but I hope you get the idea. Okay, so this is step 1 in the Gram-Schmidt procedure to orthogonalize the column in U relative to all the previous columns. And then the second step is just to normalize. That one is much easier. So we just take this column, set it equal to itself, and divide by the norm of that column. And, if you want, you could cut this out. You could do it like this. Sometimes when you're writing code, you want to be as compact and efficient as possible, but I don't believe that compactness is the end-all be-all result of coding. In many cases, it's better to have slightly more code to make it clear. All right, so all of this is the Gram-Schmidt algorithm. It's not super complicated in the sense that it doesn't require a lot of lines of code, but it is pretty tricky. This orthogonalization part gets pretty hairy. Okay, so all that explained. Now we have the QR decomposition from NumPy, and basically we're going to compare Q and Q2. Now we expect those to be identical to each other, but as I mentioned in when I was showing the PDF, there are these sign flips. So you're going to get cases where individual columns are the same numerical values, but the signs are all flipped. Now, this is actually fairly unusual, but not impossible. It turned out that all of the columns were flipped. So Q minus Q0, if these are identical, they should be, this should be a matrix of zeros. But in fact, it's a matrix of non-zeros. But when I say Q plus Q2, that turned out to be a matrix of all zeros. So that means that my Q here from Gram-Schmidt and the Q from numpy.linalg.qr ended up being identical matrices, just flipped in sign. I can actually show you that here. So let's do Q and Q2, and then you will see that all the numbers are identical and the signs are exactly flipped. Now, it's not the case that every single column has sign flipped. So I'm going to run this again. Now we have just a new, obviously the code hasn't changed, but what has changed is just these random numbers. So now you see that columns 1, 3, and 4 are identical, and column 2 is numerically the same, but the signs are flipped, and that's why you get zeros here. So as you are working through this code, what you should find, if your code is correct, what you should find is that every column has all zeros in one of these two. So I know it's weird, it's confusing. I apologize on behalf of linear algebra. I did not invent linear algebra, nor did I invent the universe that we live in where linear algebra was invented. It's confusing. I promise it's going to make more sense in chapter 13 when you learn about eigendecomposition.